This is the Amp Hour Podcast. Released June 23rd, 2018. Episode 397.6. An interview with Matt Knight. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Matt Knight. I'm a electrical engineer, software engineer, and security researcher who's worked in wireless for the last couple of years.
Welcome, Matt. How you doing?
Pretty good.
We are at beautiful Tour Camp, looking out over the Prime Dome and enjoying the quiet of the morning before all the craziness starts up again.
Beautiful San Juan Islands, perfect day.
Yeah.
Not a bad way to spend a weekend.
Yeah, not bad at all. So, what you are here with some friends and also just learning about other new realms and new people?
That's right. I missed TourCon in 2016, and at that time a bunch of my former colleagues went, and it just sounded like a great event. So when this one rolled around, I made sure to not miss it.
Yeah, this camp's great. Yeah, it's been good crossover group too. That's just weird, right? Because some of the hardware people I know here, like SDR people, are here. There's obviously just software security people, so it's a good crossover.
Yeah, for sure. And there's a nice mix of old and new. The whole Tour Camp crew is interesting because they've been running it for so long that they really do have like some institutions that have built up around it.
Right.
You've got like the Shady Tel crew obviously running around like with like old school phone wire, like setting up their playing phone company for the weekend. But then you also have people bringing in all sorts of new challenges and things like that.
Right.
So it's just fun to see kind of the legacy that's been established, but also people bringing the new ideas to the table and playing with fun stuff.
Yeah, so you are mostly an SDR these days, right? That's kind of the space you work in?
More or less, yeah. So I used to do it professionally. I'm now working in AppSec professionally. But
sorry, what's that? Sorry.
Oh, sorry, application security.
Got it, thanks.
Just general software security for a company in the Bay Area. But that means that I've got the bandwidth to double down on SDR and radio applications, radio research on the side. So been having a lot of fun with that.
That's great. And I think we mentioned you on the show before because of the LoRa presentation you had given and like the research you had done around SDR applied to LoRa type stuff.
Yeah, I guess so. So back in 2016, early 2016, I got pretty interested in LoRa and Sigfox and all these LPWANs, low power wide area network technologies that were coming out. For the unordained, you can think of them as basically being like cellular networks, but optimized for like embedded applications. So very low data rate, long range, low power, so that you can run devices on batteries for a very long time. Yeah. And one of the things that I thought was particularly interesting about them is they tend to use like very unique physical layer implementations, whereas in telecommunications like these days, you see a lot of like FSK for like IoT and like inexpensive home devices, and then a lot of like OFDM type modulations for things like Wi-Fi and cellular, kind of more professional things. And the LoRa modulation in particular was interesting because it was something totally unique. It uses what's called chirp spread spectrum, which is more akin to radar than to any sort of like digital communications technology. Right. It was also a closed standard, so I spent a couple of weeks reversing it, and then had a fun time kind of publishing it, presenting it. Actually, I re-implemented it in GNU Radio, so there's a open source implementation now that was really fun to work on. So it was just a mix of interest and good timing that this technology was kind of hitting the market, and happened to just line up well. So it was fun. Yeah, the chirp spread spectrum stuff. That is like basically the way you have a 0-1 is the frequency increasing or decreasing, right? Exactly. Sort of. Yeah. LoRa is a little more complicated because it's not just increasing or decreasing. They actually. So the way to kind of abstract it is it's like frequency modulated frequency modulation, whereas rather than having with an FSK protocol, you'll have a static carrier like a static carrier that you'll modulate to different frequencies.
Right, and that's frequently shift keyed. Right?
That's right. Excuse me. I should define my terms.
That's okay.
So you'll basically have two frequencies two more frequencies that the signal will shift between to represent a 1 or a 0. Whereas with chirp spread spectrum, rather than having a static carrier that you're modulating, you instead have a chirp signal, which is a signal where the frequency continuously increases or decreases. So then when you modulate that, what happens is it looks like the chirp is kind of jumping around within the channel or the band that it's occupying. So the modulation is actually the extent to which the chirp jumps. And the effect of that is rather than just having, if you were just measuring whether the signal was going up or down, you would have basically 1 bit per symbol. Whereas when they do it this way, they can actually have multiple bits per symbol.
Oh, got it. Okay.
So, and there are lots of different parameters you can tweak. So the end result is by playing with the phi, they can really encode the data and make it very resilient.
Right, and that's what allows for the low power. You can spread out the time base over as well, right? So,
exactly. Yeah. So we're talking about like very low data rates, very small datagrams.
Right, and that's one of the things that I heard. So we also met at the Things conference, the conference I went to in Amsterdam. We had, oh boy, I'm gonna forget his name now.
Johan Thomas.
No, sorry, one of the guys that was at TWTG. Oh man, I'm sorry, Ken. I'll try and edit in later. But he was on as well. Richard. Geez. Richard was on the show talking about some of this stuff too. That's kind of how I got into it. And then you and I met there as well. And
that's right, small world.
Yeah, and so that seems like one of the things where that is one of the limiting factors for people who are like, oh, I love the low power thing, but they're like, oh, I can only get a packet out, a minute or whatever.
But that's okay. When you look at so many applications that are coming online these days, all these IoT devices, maybe all you need to do is represent a state change. Maybe you're sending up.
Right. The switch is on. The wire is tripped. The whatever. Right.
Exactly. Or sending it down. These are bidirectional. So, or at least LoRa's bidirectional.
Yeah.
So maybe all you're trying to do is say, tell me the temperature every 10 minutes.
Right. Exactly. Yeah.
Or you can think of some more industrial applications, traffic light synchronization, things like that.
Sure.
But a lot of these have, pretty interesting security implications.
Yeah. So, what about that then?
So full disclosure, I've spent most of my time looking at LoRa. I've been pretty much exclusively focused on the physical layer, just because I'm a radio nerd, and that was particularly interesting. There is a layer 2 standard called LoRaWAN, which does define a security topology as well as a cloud architecture for how you can basically define 2 layers of keys, one that's managed by the network provider, but another that can be fully end-to-end, embedded device to the application server, fully encrypted.
And that's kind of what Things Network is at the LoRaWAN layer, right?
Yeah, exactly. So the Things Network is basically providing all that back-end architecture. I guess they have a gateway now, so they're getting closer to the device.
Sure.
But originally, when it started, they were providing all of the cloud-based back-end, so that if you wanted to provide LoRaWAN service in your physical area, you could basically get yourself a LoRa radio, run their software stack, point it at their cloud, and then you'd be able to plug your local device in to their service and all that comes with it. Of course, with all the security they built in, it is, I believe it's opt-in, and they leave bits and pieces of it up to the implementer to get right.
Right.
I can't speak fluently about that just because I haven't really spent much time researching it.
But are you saying that there are some physical security issues as well?
I'm not going to make that claim.
Okay.
Just because, a phi's a phi, there are...
I mean, you could snoop any signal off with an SDR, right? But it's all about can you back calculate to what the hell they're sending in the first place, right?
Right. Yeah. So the phi itself provides some scrambling and obfuscation, not for the purpose of providing security, but for providing resiliency. All that stuff that you can reverse, right? Which I did. I think what's interesting is there are some features in the LoRa physical layer that could lend themselves to certain geolocation applications.
Oh, cool.
The fact that the widest LoRa channel supported is 500 kilohertz. It's reasonably wide. If you had enough receivers and were doing, some sort of TDMA-based localization, you could probably drill down the location of a LoRa device to being pretty accurate.
Yeah.
Something I haven't done yet, but it's something
kind of fun though, like a cheap beacon kind of idea.
Exactly, yeah. But obviously, if that's possible, then that's useful for benign applications, and also,
right. Any tool can be turned into a weapon, right?
Exactly.
Yeah.
But this is all theory at this point. I don't want to spread FUD. I'm just saying
yeah,
that
that's fine.
look, the properties of the signal could lend to some interesting applications like that.
That's cool. So let's take a step back. So how did you get into this radio space? I mean,
yeah, sure. So if you go back far enough, I'm not that old, right? But,
no, I don't believe he looks ancient, folks.
If you go back to college a couple of years ago, I got an electrical engineering degree from Dartmouth, and mostly studied, digital electronics, embedded systems, things like that. I did have a course where one of the labs was building a digital radio receiver.
Cool.
So kind of got a little bit of a taste there, but I didn't really start drilling into SDR until a couple years later. I was working my first job in the DC area just as a general purpose embedded software developer for a home automation company, and I really wanted. Excuse me, I was working on specifically wireless networking stacks.
Got it, okay.
And I really wanted the ability to do some more introspection, spectrum, just keep an eye on what was going on. And at the time, the Hacker F Jawbreaker had just come out. It was the prototype to the Hacker F1.
Yep.
And there was some more open source activity. So I was thinking, this could be an interesting way to get like a this could be like a poor man's spectrum analyzer type
Exactly,
thing.
right. I mean, you just need more I mean, it's like this thing that goes off in the ether, and it's like, oh, I hope that worked.
Exactly, yeah. And that's a really interesting point. Is like so many developers, whether they're working on wireless networking stacks or they're like writing network code, they get to the point where they call, driver.send.
Yep.
They pass in a pointer and a length value, or just interface to another piece of software, and they pass it off, and at that point, you don't really quite know what's going on.
Exactly. You need that sanity check at some point, and without the tools, the sanity check is usually a $30,000 piece of equipment from Agilent, right?
That's right, yeah.
It's like, oh, okay, that might work if I have that dollar. So that's great.
Exactly. Or you can buy an RTL SDR and or something like it.
Right.
So I got my hands on a Jawbreaker and was using it for some of those simple applications, but it didn't take long to realize that the fact that it could transmit and receive, or transmit in addition to receiving, the implications became clear that this technology was in a way invalidating my prior model of working on wireless networking applications.
Right. The hand it off and hope for the best.
Exactly.
Yeah.
Well, not just that, but also working on fixed protocols too. The fact that
the
protocol.
Right. You're handed Bluetooth, and it's like, nope, not anymore.
No, in fact, you're handed. You're handed the IC manufacturer's interpretation of Bluetooth.
Right, that's a good point, actually. And I didn't realize that for a long time. That it's like, even though there are standards bodies and there are these specs, it's like it's just as good as you want it to be.
Well, so I think when you're talking about standards, you're really talking about abstraction, right? And the way that standards get developed and then implemented is it can be perilous. Not wanting to spread FUD, but it's just very complicated the way that it works. So you have all these industry stakeholders that decide that they want that the way of doing things isn't optimal for what the current way of communicating or the current way of implementing a certain technology isn't optimal. So they get together and they go back and forth and define a standard. And they turn their consensus into several thousand pages of documentation. That gets handed off to manufacturers. That may be open. It also may not be.
Oh, really?
It can be proprietary, right?
I thought you said opened. You mean open to the public versus closed to the...
Right, exactly.
Right. I thought you meant like they don't open it up. They just do whatever they want anyways.
Again, it depends, right? Some of these standards bodies are a lot more transparent than others.
Yeah.
But anyway, this process is very dry, right?
Yes.
So they take this consensus, turn it into a big data sheet.
Yep.
They hand it off to the manufacturers, and the manufacturers will have to turn that into silicon or a software stack. They have to implement it, right? And that even the best defined specs are not going to be complete. There might be something that's left up to interpretation or cases that aren't fully closed off. And what that means is that when they're developing these implementations, they're really interpreting the spec as much as they're implementing it.
Yeah.
And that gives rise to discrepancies among chipsets and implementations and things that you can fingerprint and then potentially exploit.
Oh, so, interesting. Okay.
I'm actually giving a DEF CON talk about this later this year. It's all about fuzzing RF physical layers to find these different corner cases within PHYs.
Could you explain what fuzzing is real quick?
Oh, sure. Yeah, certainly. So fuzzing is it's a technique that's often used by security researchers to automatically and programmatically find bugs in systems. Essentially, what you do is you define a black box, kind of an input and an output, and then you generate random or pseudo-random input to that, and then measure its state as the system responds. So an example might be you may have like say a networking stack, and you want to know if it's closed off and is reasonably secure. So what you can do is you can start with a packet, a well-formed packet, send it in, make sure that the stack doesn't crash, and then you can mutate that packet. You can start flipping bits and doing things to change it, and send it in and see what happens.
Okay. So it's kind of it's like a test bench, right? Of like
exactly.
Inputs and outputs, and you have some guess at what's going to be a potential good start, right?
Exactly. Yeah. It's often used to enumerate crashes, and then you'll basically log things that either fit a certain heuristic or things that you want to go back and look at because they might be interesting or contain exploitable crashes. But with the on the RF side, what we're looking to do is we're really looking to characterize differences between receivers. So to do that, my collaborator and I, there's a guy, Ryan Spears, I know him from Dartmouth, does some really interesting work in the security space as well. He and I wrote a fuzzing framework called Tumble RF, or TURF for short, that basically abstracts the fuzzer and the radio driver to make it easy to implement other radio ICs, integrate them into this into this fuzzing framework, so that we can fuzz them programmatically. And if people want to learn more, really the seminal paper about this actually came from a research group that Ryan was affiliated with at Dartmouth. I want to give them full credit because they were the ones that really turned us on to this.
Yeah.
And that was, I believe it's called Speaking the Local Dialect. And it came out.
That's great.
Came out in 2011 or 2012. It's a really good read, and certainly opened my eyes to a new way of looking and thinking about FIs. So I want to make sure I give them credit for that.
That's great. No, that's great. So now, I mean, it sounds like you're building some tool sets around that research, right? So
exactly.
That's we're science, and then into engineering world, and then into the
Exactly. Yeah, we're trying to get it into a form where others can pick it up and run with it as we have.
So what do you expect people would do with that kind of thing then?
So here's an example. At the company I used to work at, one of my colleagues, Mark Newland, found a whole bunch of vulnerabilities in wireless mice and keyboards.
Oh, yeah. Okay.
And a component to doing that was fuzzing. He set up a fuzzing setup where he could send 2.4 gigahertz RF transmissions at these dongles and then monitor for HID, like a human interface device, state changes on.
Right.
Like,
does it type a letter when it's not supposed to, right?
Exactly. Yeah. Does this random message produce character output
that's great.
On the computer? But to do that, he had to write a fully custom framework. He had to write all the software for monitoring both the state of the transmitter, the state of the receiver, making sure that after each test case, the system was still in a valid state.
Because you're kind of like deep into a state machine. Is that kind of the idea?
You can be, right? Yeah. So you want to. In the other thing is you might not have full knowledge of what that state machine is.
Right.
So
does it respond to command A or command B?
Yeah. So you might do things like send a fuzz test case, see what happens. You might get no response, but then you may follow it up with a known good test case. So you would expect that to succeed.
Right.
So you design your tests in a way like that so that you can basically hands off, automate, and let the system self-monitor.
Right.
But so back to Mark's story, he wrote this. He wrote this custom fuzzer to help him do a lot of this. But if he were to want to say fuzz Bluetooth Low Energy, he would then have to replicate a lot of that work. Presumably, he's a great software engineer, so he would have done a lot of abstraction to make it easy to do that.
Yeah.
Just one example of a type of project that could instead be implemented on our framework in a way that would save a lot of time and effort going forward, because we basically implemented all of the fuzzing and the coordination logic, and all you have to do is basically take the radio driver that you want to fuzz and just hook it into our abstracted API.
Nice.
It's like 10 function calls that you map in.
That's awesome.
And you're off to the races.
Right.
Most of the files are like 100 lines of translation.
Well, I imagine some of this stuff, if you were building up the stack yourself too, there's a chance that if you introduce your own bugs that then could ultimately impact the fuzzing process, and that could be problematic. So if you have a standard base to start from, that's helpful.
That's right. Yeah. If you're building something like this, it's probably not because you think that fuzzing engines are the most interesting thing in the world. Maybe
Right.
maybe you do, but maybe you're doing it to facilitate your your exploration of another system.
Right.
So.
That's great.
Yeah, so we open sourced it earlier this year, and we're excited to be able to bring it to DEF CON and show it off there. We'll be at Black Hat Arsenal too with some more applied demos.
And so that's a software-based tool.
Exactly.
Is there also a hardware component to it, or is it using off-the-shelf hardware, or what?
Yeah, so good question. So the software stack, Tumble RF, is hardware agnostic.
Okay.
So you can bring whatever hardware you'd like to it. We have some demos built up on 802.15.4 that use a mix of kind of conventional hardware radio ICs as well as an SDR.
Okay.
I use the SDR to generate test cases because it's this nice mutable. It's this nice because the entire PHY is in software. It's very easy to mutate all these different cases.
I see.
And then the ICs that we were testing were obviously hardware ICs. In addition to the software framework, I do have a hardware project I've been working on, which we're aiming to have a prototype ready for DEF CON. It's a 2.4 gigahertz fuzzing board that I, for the time being, have codenamed Orthrus.
Okay.
It's a Greek mythological figure. It's a two-headed dog.
Gotta have a good name. Yeah.
You gotta have a good name.
Yeah.
But the reason why I went with that is because this radio board has two front ends. So that it can do some very fast, transmit and receive applications to get around some limitations of the chip that I'm using.
Okay.
Mode state transitions are kind of slow, so
Got it.
get around that just by using two.
Got it. That's
Yeah.
really
So the intent there is, or the kind of the motivation here is twofold. First of all. One of the major limitations of consumer software-defined radio devices is the fact that most of them are exposed over USB interfaces.
Okay.
And USB brings with it latency. You're typically looking at least a millisecond of round trip time, which in the radio domain is a very long time because symbol periods are short. Data transfers happen really fast. So if you want to have any stateful or responsive either inspection or response, that latency can be limiting.
Could you give us a tangible example of that? So
Sure. Yeah. So let's talk about like 802.15.4 for instance. I don't have the numbers handy, but an 802.15.4 packet, can be up to 127 octets of data at the MAC layer, along with a 6-character PHY or 6 octet PHY preamble, I believe.
Okay. So just long strings of bits, right?
Not that long though.
Okay.
Yeah, it's strings of bits. An 802.15.4 ACK is only 5 octets long, so it's quite a bit shorter. And there are within the standard certain response intervals that where if you receive a packet, you're supposed to ACK it within a certain amount of time before the transmitter will assume that the message wasn't received. For applications like that, the USB latency can be too long.
Got it.
In certain cases. Beyond that, if you're trying to do things like front run ACKs or do like low level, very timing sensitive security applications, that 1 millisecond of latency can be a killer.
Got it. And so this is kind of like a man in the middle type thing, or is that kind of the idea? Is like you receive data and then you want to send back an ACK even though it's not necessarily getting to the point it thinks it is, or
that's one type of application.
Okay.
Right?
Okay.
Again, I'm trying to think more generally. Part of it is just motivated by some limitations that in the course of doing my wireless research I have encountered that I've wanted to get around.
Cool.
The other thing is because we're in the 2.4 gigahertz band and we're using a really interesting IC, it's going to be possible to implement different radio physical layers using very software-defined radio-like methodology, but in a hardware-defined radio format. So the chip I'm using in particular, it's an analog devices chip that enables you to bypass basically protocol decoding and framing and get raw symbols out of it.
Oh, okay.
Which means that a lot of what I've been using software-defined radio for in the past, I'll be able to instead implement hardware-defined radio and have.
That means FPGAs or?
Actually, no. It's just built around a really cool feature in this chipset.
Okay.
So we'll be able to do it on a small board and work across protocols in a more flexible and quickly iterable way.
Right.
Also cheaper too. SDRs are expensive. They're getting cheaper, but the hope is that this board will be pretty inexpensive and enable researchers to do some new kind of interesting performance-sensitive wireless stuff. Whatever have you.
That's interesting. I really like the thing you said about I never thought about SDRs as like implementing the PHY in software. Like that's a great selling point for it, but I've never had a phrase like that in my head.
So one thing I always try to emphasize whenever I'm either teaching about SDR or doing trainings or whatever is that like software-defined radio isn't a product; it's an architecture. And there are boards built within like a software-defined philosophy where you have that like abstraction well serviced by the design of the board, but it's not like when you buy a Blade RF or a USRP, like that's not like there's no standard called software-defined radio.
Right. Where's the button?
Yeah, exactly.
Where's the SDR button?
And once you get past the driver and the host, it's just data. SDRs are basically just sound cards for capturing raw RF and offloading that to a host. So it really is all about pushing that hardware implementation into a software abstraction.
Okay. Yeah, that's great. Cool. So, I mean, it sounds like you got some good stuff coming up. Where can people find out more about you online or your past research or anything like that?
Sure, yeah. So you can find me on GitHub, just Matt-Knight, so github.com/Matt-Knight. I have a repo called Research that I try to keep all my past like slide decks and links to videos and things like that in. I'm pretty delinquent in updating it.
Yeah.
I know I've got some stuff on there that I need to, or some stuff that's not on there that should be on there. You can also find me on Twitter. I'm at EmbeddedSec, like embedded SEC. And always, reach out. Happy to hear from people, and I'd be happy to meet in Vegas, Black Hat, DEF CON, if any of this stuff is interesting.
Yeah.
I'll also give a plug for GR LoRa, the software-defined LoRa implementation I made.
Yeah.
I wrote it about 2 years ago, and just spent the last 2 years like pretty thoroughly neglecting it.
But maybe you're back to it, huh?
I'm gonna, I've got some time carved out after Black Hat and DEF CON to keep working on that, and I'd love to, have some collaborators on that. So if
great.
This sort of thing is interesting and you want to reach out, I'd love to hear from you.
Awesome. Well, thanks for being on our short amp hour stuff from Tour Camp. We'll have more talks here in a couple more days. A couple days left.
Thanks, Chris. It's great to chat.
All right.